Detroit Diesel believed their two-strokes would last forever. But near the end of the 80s, something happened inside their own test labs that shook that confidence. Engines that had dominated for decades were suddenly showing weaknesses that Detroit wouldn't talk about publicly. Mechanics were noticing issues that didn't fit the engine's reputation, fleets were reaching uncomfortable conclusions, and a quiet shift inside the company signaled the end of an era. And it wasn't just emissions that pushed these engines to the brink. What Detroit discovered in those final years changed the future of the company. This is the story of why Detroit Diesel quit making their two-stroke engines. In 1943, a pair of Detroit Diesel 671 engines fired up inside an M4A2 Sherman tank, grinding forward on an Allied front. That same year, another 671 powered a landing craft hitting the beaches of the Pacific. By war's end, Detroit Diesel had produced over 57,000 engines for the Allied war effort, one every 10 minutes at peak production. From the late 1940s through the 1970s, Detroit Diesel's two-stroke engines didn't just shape American industry, they became one of its defining sounds. The Series 71 family powered Greyhound buses crossing the country and long-haul truckers pulling 80,000 pounds over the Rockies. Construction crews relied on 8 V71s in their cranes and bulldozers. Farmers trusted 671s to run irrigation pumps through brutal harvest seasons. The engines earned their reputation through brutal simplicity. Unlike four-stroke diesels that fired every other revolution, Detroit's two-strokes fired on every stroke of the piston. More power strokes meant more power from a smaller, lighter block. Every one of these two-strokes came with a roots-type blower, not as a performance option but as a requirement for scavenging. The blower forced fresh air into the cylinders, pushing the burnt exhaust gases out through the exhaust valves, the scavenging process, creating the distinctive high-pitched whine that became known as the Screamin' Jimmy. This wasn't just mechanical noise, it was the sound of American industrial might. Dock workers could identify a Detroit-powered tugboat from miles away. Construction foremen knew their equipment was running right when they heard that unmistakable roots blower whine echoing across the job site. What made these engines truly legendary was their tolerance for abuse and neglect. Fleet mechanics discovered that Series 71 engines could handle overloads, poor maintenance, and operating conditions that would destroy other power plants. The unit injector fuel system meant no complex fuel pumps or high-pressure lines to fail. Individual injectors could be swapped in minutes with basic tools. The mechanical blower was about as simple and rugged as it gets. Just gears, rotors, and a cast-iron housing that could run an incredible number of hours with minimal attention. Parts availability was another crucial advantage. Whether you needed pistons for a 371 powering a generator in Alaska or connecting rods for a 16 V71 in a Great Lakes freighter, Detroit Diesel's modular design meant components were interchangeable across most of the engine family. A mechanic in rural Montana could rebuild a 6V92 using the same techniques and many of the same parts as his counterpart working on tugboats in New Orleans. Fleet operators bought Detroit engines in bulk, knowing they were investing in proven technology. Greyhound operated thousands of buses powered by 8 V71s, accumulating millions of miles with minimal downtime. Construction companies standardized with Detroit Power because mechanics could service any machine in the fleet with the same knowledge and tools. By the mid-1970s, Detroit Diesel had achieved something remarkable. Their two-stroke engines had become synonymous with dependability itself. Mechanics and fleet managers joked that these engines would outlast the company itself, after watching Detroit two-strokes accumulate hundreds of thousands of hours while barely breaking stride. But outside the world of heavy equipment and long-haul trucking, fundamental changes were reshaping the diesel engine industry. Fuel prices were climbing. Environmental regulations were tightening. Most importantly, competitors were making breakthrough discoveries in four-stroke diesel technology that would challenge everything Detroit Diesel thought they knew about engine design. By 1978, something had shifted in the heavy-duty trucking world that Detroit Diesel's engineers couldn't ignore. Fleet managers who had once bought engines based purely on horsepower and reliability were now asking different questions. How many miles per gallon? What's the maintenance cost per mile? How much downtime for service intervals? The oil crises of 1973 and 1979 had fundamentally changed the economics of commercial transportation. Fuel costs that had once been a minor line item in fleet budgets suddenly represented 25 to 30% of operating expenses. Owner-operators who had previously chosen engines based on sound and reputation were now calculating fuel economy down to tenths of a mile per gallon. Detroit's two-stroke engines, designed in an era of cheap fuel, began showing their age in this new economic reality. The Series 92, introduced in 1974 as a larger displacement evolution of the 71 series, was built to deliver more power for heavier long-haul and industrial work, while nudging fuel economy and emissions in the right direction compared to earlier two-strokes, but it still lagged behind emerging four-stroke competitors. Internal company testing revealed uncomfortable truths. Cummins' new big cam engines were consistently returning noticeably better fuel mileage in over-the-road applications, where Detroit's 8V92 was already working hard to crack the mid-6 miles per gallon range. The fuel economy gap wasn't the only concern troubling Detroit's engineers. Field reports were documenting new types of problems that hadn't plagued earlier two-stroke generations. The Series 92's turbocharging system, designed to boost power and efficiency, proved sensitive to maintenance and operating conditions. Mismatched turbochargers could cause excessive exhaust gas temperatures, leading to piston and cylinder head problems that were expensive to repair. Rack adjustment issues became a persistent headache for mechanics. The two-strokes fuel injection system required precise calibration to achieve optimal performance. But the precision required for timing and calibration of the mechanical fuel racks and unit injectors was prone to wear and maladjustment. A slightly out-of-spec setup could cause uneven cylinder firing, excessive smoke, and poor fuel economy. Airbox problems emerged as another troublesome pattern. The Series 92's air intake system, more complex than earlier Detroit designs, proved vulnerable to contamination and seal failures. Dirty air filters or leaking airbox seals could cause the engine to ingest debris, leading to accelerated cylinder wear and reduced service life. Overheating tendencies in certain applications raised additional concerns. The Series 92's higher power density and turbocharging created more heat than earlier naturally aspirated engines, requiring more sophisticated cooling systems. In demanding applications like heavy construction or steep-grade trucking, some operators reported cooling system problems that had been rare with previous Detroit engines. Detroit Diesel's management initially dismissed these issues as growing pains with new technology. Internal memos from 1979 characterized the problems as field adjustment issues that would be resolved through improved service training and parts availability. The company's leadership, steeped in decades of two-stroke success, viewed the complaints as temporary setbacks rather than fundamental design limitations. But in the engineering departments, a different conversation was taking place. Test data from Detroit's proving grounds showed that competitors weren't just matching Detroit's performance. They were exceeding it in key areas. Caterpillar's 3406 engine was delivering superior fuel economy and lower maintenance costs. Cummins' Big Cam series offered better torque curves and longer service intervals. Internal company reports from 1980 documented the widening performance gap. In controlled testing, Cummins' NTC 400 engine turned in clearly superior fuel economy compared to Detroit's 8V92 in identical applications. Caterpillar's 3406B showed 15% longer intervals between major overhauls. The data was undeniable. Detroit's two-stroke technology was falling behind. Even more troubling was the realization that the fundamental architecture of two-stroke engines limited how much these problems could be improved. The scavenging process that gave two-strokes their power advantage also meant that some fuel inevitably passed through unburned, reducing efficiency and increasing emissions. The mechanical simplicity that made two-strokes easy to service also made them difficult to optimize for the precise fuel delivery and timing control that modern applications demanded. By 1981, Detroit Diesel faced an uncomfortable truth. The same design principles that had made their engines legendary were now becoming liabilities in a rapidly changing market. Inside Detroit Diesel's engineering offices, a small team of engineers had already begun working on something that would change everything. A clean sheet four-stroke design that would eventually become the Series 60. The meeting took place in a windowless conference room at Detroit Diesel's headquarters in December 1982. Around the table sat the company's top engineers, clutching folders marked confidential that contained test data from a prototype engine designated internally as Project Greenhouse. What they were about to discuss would fundamentally alter the trajectory of American diesel engine development. The prototype wasn't a two-stroke. For the first time in Detroit Diesel's 44-year history, their engineers had built a four-stroke diesel engine from the ground up. The early test results were stunning and deeply troubling for anyone invested in two-stroke technology. In fuel economy testing, the four-stroke prototype pushed highway mileage well into the upper 7 miles per gallon range in applications where Detroit's best two-stroke, the 8V92, typically lived in the low sixes. That kind of jump wasn't a marginal gain. It represented a fundamental shift in operating economics that fleet managers couldn't ignore. But fuel economy was just the beginning. The four-stroke prototype ran significantly quieter than any two-stroke Detroit had ever produced. Sound level measurements showed the new engine operated at 78 decibels under load compared to 89 decibels for a comparable 8V92. An 11 decibel reduction translated into a dramatically quieter engine to the human ear, enough to transform the driving experience for long-haul truckers and eliminate noise complaints from urban bus operations. Durability testing revealed another advantage. The four-stroke's more controlled combustion process reduced thermal stress on engine components. Preliminary projections suggested the new engine could stretch overhaul intervals out towards 750,000 miles, compared to the roughly 500,000-mile targets Detroit quoted for its best two-strokes. Most significantly, the four-stroke design offered something two-strokes couldn't match: precise electronic control over fuel injection timing and quantity. Early experiments with electronic fuel injection showed the potential for optimizing combustion in ways that mechanical fuel systems simply couldn't achieve. Each cylinder could receive exactly the right amount of fuel at precisely the right moment, maximizing efficiency while minimizing emissions. The implications were staggering. An engineering manager summed up the findings with this statement: "We're not just developing a new engine, we're developing the engine that will make our current product line obsolete." The realization created an internal crisis at Detroit Diesel. The company had invested decades and hundreds of millions of dollars perfecting two-stroke technology. Their manufacturing facilities, supply chains, and service networks were all optimized for two-stroke production. Now, their own engineers were proving that a completely different approach was superior. The decision to proceed with four-stroke development wasn't driven solely by environmental regulations, as many industry observers later assumed. EPA emission standards in 1982 were far less demanding than what was coming in the 90s, and Detroit's two-strokes could still be made to meet the existing limits with a mix of calibration changes and hardware tweaks. The real driver was market pressure from fleet operators who demanded better fuel economy, lower noise, and reduced maintenance costs. The breakthrough came in 1984 when Detroit's engineers successfully integrated electronic fuel injection with their four-stroke prototype. The Detroit Diesel Electronic Control System, or DDEC, represented a quantum leap in diesel engine technology. Unlike mechanical fuel injection systems that delivered fixed quantities of fuel based on throttle position and engine speed, DDEC could adjust injection timing and quantity based on dozens of operating parameters measured in real time. The results were revolutionary. DDEC-equipped prototypes achieved fuel economy improvements of 15 to 20% over mechanically injected engines. The system could optimize combustion for different operating conditions, maximizing power for acceleration, minimizing fuel consumption for highway cruising, or reducing emissions during idle. By 1985, Detroit Diesel faced a stark choice. EPA regulations scheduled to take effect in the early 1990s would require significant reductions in nitrogen oxide and particulate emissions. Meeting these standards would require substantial investment in engine development. The company could either spend hundreds of millions of dollars trying to make two strokes cleaner, or invest that money in perfecting their four-stroke design that was already proving superior in every measurable category. The decision was made in a boardroom, not an engineering lab. Detroit Diesel would bet their future on the Series 64-stroke engine. Development funding for two-stroke improvements was quietly redirected to the four-stroke program. The legendary engines that had built the company's reputation would be allowed to fade away, replaced by technology that their own engineers had proven was simply better. Detroit Diesel didn't lose their two-stroke engines to emission standards. They lost them to progress and to an engine of their own design that proved the future belonged to four-stroke technology. The end came not with fanfare, but with the quiet removal of model numbers from sales brochures. In 1987, Detroit Diesel introduced the Series 64-stroke engine to widespread industry acclaim. Fleet managers praised its fuel economy, drivers appreciated its quiet operation, and mechanics welcomed its electronic diagnostics. What few noticed was that Detroit had simultaneously stopped promoting their two-stroke engines to new customers. The transition happened faster than anyone expected. Greyhound, one of Detroit's largest and most loyal customers, began specifying Series 60 engines for their new bus orders in 1988. After decades of operating 8V71-powered coaches, Greyhound's mechanics were initially skeptical of the electronic four-stroke engines, but real-world experience quickly converted the doubters. The Series 60 buses achieved 20% better fuel economy while running significantly quieter, a crucial advantage for passenger comfort and urban noise ordinances. Long-haul trucking fleets followed similar patterns. Companies that had standardized on Detroit two-strokes for decades began transitioning to Series 60 power as soon as sufficient quantities became available. The fuel economy improvements were too substantial to ignore. A typical over-the-road fleet operating 100 trucks could save over $200,000 annually in fuel costs by switching from 8V92 to Series 60 engines. By 1990, Detroit Diesel had quietly discontinued most two-stroke models from their standard product line. The Series 71 engines that had powered American industry for 5 decades were relegated to special order status for specific applications. The Series 92, once Detroit's flagship highway engine, disappeared from truck catalogs entirely. The relatively simple mechanics that had made two-strokes legendary became a liability in the electronic age. Fleet managers wanted engines that could communicate diagnostic information, optimize performance automatically, and integrate with computerized maintenance systems. Mechanics who had spent their careers working on two-strokes faced a difficult transition. The intuitive mechanical systems they understood intimately were being replaced by electronic controls that required new diagnostic equipment and training. Many older technicians retired rather than learn computer-based engine management. The cultural impact extended beyond professional mechanics to owner-operators and equipment enthusiasts who had formed emotional attachments to two-stroke engines. Despite the nostalgia, the transition to four-stroke power proceeded inexorably. Fleet operators couldn't argue with fuel economy improvements of 20 to 30% and maintenance cost reductions of similar magnitude. Insurance companies began offering lower rates for fleets operating newer, cleaner engines. Their legacy survived in unexpected places. Marine applications, where emissions regulations were less stringent and fuel economy less critical, continued using rebuilt two-stroke engines well into the 2000s. By the mid-1990s, the last Detroit two-stroke engine families were winding down on the production lines, effectively ending an era that had spanned more than 5 decades.